All right, so let's talk about how we can evaluate the solutions that we have generated. Levine has a theory of hypothesis testing that says that we use a global focusing strategy. What he means is that we can keep track of many hypotheses at the same time and then reject those that are not consistent with the feedback that we're getting. We kind of talked about this a little bit when we were talking about figuring out the rules for the shapes that I showed you in an earlier chapter, where the first one was a red circle, then it was a big red circle, then a big red square, and both of those were yes, they belong to the category. And then the next one was a small red circle, and that was a no, right? So as you're starting to develop theories, that size is the important thing or color is the important thing, you can hold many of those things in your mind at the same time, and slowly you're dropping off the ones that are being rejected by the evidence, right? So the evidence for this kind of global focusing strategy is, for one thing, adults displaying intelligence in these kinds of situations, right? That adults they clearly solve problems in ways that look like they are, holding many possible hypotheses and rejecting the ones that get disproven, on the fly. The other evidence for global focusing strategy comes from those kinds of experiments and tasks when the task is relatively simple, like the circles and squares that were either large or small, white or red, like that. When it's a relatively simple task, there's a lot of evidence that people seem to follow that kind of global focusing strategy as they solve the problem. Evidence against it is, we don't have the most, wide-ranging memory capacity. I mean, if we're going to have to hold this information in our working or short-term memory, if it's short-term memory, 7 plus or minus 2 individual items that we can hold in there. Even with working memory, they say there is limited capacity. We don't have a quantifiable number, but it's limited to some degree. How many hypotheses can we really hold in our head at one time? And how much evidence can we then be weighing against those hypotheses and manage it all at one time? So it's probably not going to work as well in the face of complex tasks. And when we see people trying to solve more complex tasks, they don't seem to be using a global focusing strategy. So the idea with the global focusing strategy is that you have a working hypothesis from the pool of existing hypotheses. When the feedback is consistent with the hypothesis, we retain that hypothesis to the next step. When the feedback is inconsistent with the hypothesis, then we go ahead and choose a new working hypothesis from the pool of candidates that is consistent with the feedback. And so maybe we cycle through those, and that might allow us to do a little bit more complex task. But this is the basic idea with the global focusing strategy, that we have predictions, right? That's what a hypothesis is. And then we test those predictions against the evidence and we work through those hypotheses. All right. So we should be really good problem solvers. And I mean, honestly, of all the creatures in the world, we probably are the best problem solvers. But we still have some shortcomings. Like, we make mistakes that seem kind of, inadequate given our cognitive capacities. You might think, how did we not see that? How did we make that mistake? Well, there are certain thinking strategies that get in the way of us being effective problem solvers. So one of those obstacles is what's called the persistence of set. Now, I told you way back earlier when we talked about perception that the word set was going to come back again. Set means expectation. And so persistence of set means that we have an expectation going into a situation. And even if the situation isn't really matching our expectation, we stick with it anyway. That set still sticks with us and is powerful. So I thought I would show you this game called the Tower of Hanoi. Now, the instructions for the game are that you're supposed to try to move all the discs from Tower 1 to Tower 3. You may only move one disc at a time. You must never allow a bigger disc to go on top of a smaller disc. Okay. Now it says the minimum number of moves required to solve this problem is 7. So even if I do it perfectly, it's going to take at least 7 moves. So that's why we're glad we're doing it with 3 discs, because 3 discs takes 7 moves. So I'm going to follow the directions. I'm trying to get it from tower 1 to tower 3. Can never put a bigger one on a smaller one. So I'm going to move it like this. Okay. And ta-da. Whoops. It didn't fall, but it says I won. Okay. All right. Now, that strategy that worked for 3 pegs and 3 discs, where you go little guy, medium guy, little guy on top of medium guy, big guy onto peg 3, little guy to the left, medium guy on top of 3, little guy on 3. Okay, that's the sequence of events. I'm going to hop really quickly to, I think the strategy changes at for sure 6. I am not going to solve this entire problem because it says minimum number of moves 63. If I go, well, I'm going to do what I did last time. Move number 1, move number 2, move number 1, move number 3, move number da-da. I think it'll end up taking me more than 63 moves because I'm actually not doing the most efficient thing I could. Right? Because look at all these moves I have to make. I have to move this back here. Then I have to move, no, I'm regressing. But no, that's okay. You have to regress a little bit. See, the strategy is different when you're trying to, I went the wrong one. No, I can't remember which one's bigger, purple or blue. Oh no, I'm so confused. Oh no. Hold on. Yeah, I know what I'm doing here. Okay, yeah. Okay, and all this just to get this guy over there. I'm already on 18 moves. The idea that we can get stuck in a strategy can cause us to actually take more moves on this problem than I need to because I'm trying the strategy that had worked when I was doing 3 discs or when I was doing 5 discs or whatever. That's persistence of set. You continue to use the strategies that have worked in the past, even as the new information tells us we need to come up with a new strategy. Let's try a different variation on this. This is called the 3 jugs problem because there are 3 jugs. So for each trial, they called it problems in this table. For each trial, you're going to be told how much volume each jug can hold. So in trial 1, we're looking at jugs A, B, C. We're told what the volume of each jug is, and we're trying to measure out this much water. Now the rule in the game is that you have to fill each jug to its top. Like you can't estimate. So you have to fill each jug up full, and then you can measure out full jugs worth. So you can discard water from a full jug, but you can't estimate. So I can't try and just pour 100 units of water into the jug B, which is capable of holding 127. I have to do it. I have to actually do it. So let's say we're on trial 1. Jug A can hold 21, B can hold 127, and C can hold 3. And we're trying to end up with 100 units. So the correct solution to the problem is to fill up jug B to its capacity of 127 units, pour 21 units into jug A, then pour 3 units into jug C, dump it out, and pour 3 more units into jug C, and you'll end up with 100 units left in jug B. Okay. So once you figure it out, you'll notice that same process works for problem 2. 46 minus 14 minus 10 is 22. In fact, it works for all the first 5 trials. 43 minus 18 minus 20 is 5. 42 minus 7 minus 12 is 23, and so on through all of them. So you start getting into a little bit of a rhythm when you're doing this exercise. And you're like, okay, fill jug B, dump into A, dump into C, empty C, dump into C again. Jug B will contain the correct amount of water. Then we get to we get to trial 6. Now 49 minus 23 minus 6 is 20. So it still works on 6, but guess what? There's an easier way to do it. Fill jug A, dump 3 units into C, and that'll leave 20 units in jug A. So why go through all those steps that you had established on the first 5 trials when on trial 6 you could just do a one-step thing? What they found with people who were participating in the study is that most people on trial 6 persisted with the same strategy that they had displayed on problems 1 through 5. It worked, so why would I be thinking something else? It wasn't until they got to trial 7, and now it doesn't work to do fill B, empty into A, empty C twice. Now suddenly they have to think about it a different way. Now you have to go fill A with 15, fill C with 3, and dump them both into B. And that's the solution. Now suddenly they got stuck and they had to come up with another solution. They had to figure that out. But trial 6, they were like still going with the standard status quo because of persistence of set. Stick with the strategies that have worked, right? Sometimes that's fine. Like, what's the difference if I wasted a little bit of time in an experiment? But in real life, you can imagine where, the more efficient strategy might be worth your while. And, opening up your mind to a different way of solving the problem might be worth your while. Now, that was a persistence of set. That demonstration I just showed you was really about, solving these kinds of sort of mechanical-ish kinds of problems, right? Like trying to figure out how much water in the jugs or whatever, or how to do the Tower of Hanoi. But what about when you have objects out in the world and one might work perfectly fine for some other task, but you are displaying what's called functional fixedness, where you can't, no, that object is used for that. Like, you don't use it for something else. That object has a function, and that function is fixed. That's what we do with that object. I'm the queen of functional fixedness, so I'm not trying to cast any aspersions on anybody. I'm the queen of it, so there are a lot of demonstrations. But one is, I have this spray bottle that I use to squirt onto like 100% cotton clothing that is really stuck with wrinkles, and I want to get them out. I'll spray that water on it and then iron it, but it's too tall to be filled in the bathroom sink. So I was in my second-story house. I was trundling down to the kitchen where it has a taller faucet to fill the bottle, and my husband goes, "Why don't you just fill that in the bathroom?" And I kind of condescendingly said, "It doesn't fit in the sink." And he goes, "What about the bathtub?" And I'm like, wait a second, fill a bottle with the bathtub faucet? Hold on. It never occurred to me. The bathtub is for filling the bathtub. It is not for filling bottles, obviously, right? Like I do so many of those kinds of things. When I see somebody else, using an object in its non-intended purpose and such a smart use of it, I'm like, oh my gosh, I never would have thought of that. I am the queen of the functional fixedness. So I thought I'd display this for you by, first off, reintroducing you to this object called a record. Back in the olden days, we had record players, and, if you wanted your record to play a comedy album or music or whatever, you had to put the needle down on the record and it spun and it played the sounds for you. What if I gave you a record, a tablet of paper, some Scotch tape, and a sewing kit? Would you be able to make music off of this record that contains music on it? Could you actually solve that problem? I'll just tell you right now, I would say for me, no. But I've seen the solution, so now I can proudly say, oh yeah, it's totally solvable. Now that I know how. And some of you might have had a science teacher who showed you how. I will stop talking here and I will let you see how those objects can actually make a record player. So enjoy that. I'll see you on the other side.